So for problem I believe you can reverse, what are you given, numbers?
Yeah.
You're given some numbers and you want the numbers to be in sorted order, right?
Yep.
And you can reverse one continuous subsegment of it. Is that right? Is that what the problem's asking?
Mm-hmm.
And you wanna be able to tell if you can do it or not. If you can reverse some subsegments so that the list is sorted. So if the list is sorted, then you can do it by reversing a subsegment of length 1, so from 1 to 1. And if the list is not sorted, then you can find the first time where there's an inversion. So if you have something like this, and then you might want to find the last, so the first time, the first inversion is here, and the last time there's an inversion, so maybe you have another inversion here, and you want to reverse this subsegment, I believe, and if this subsegment gets, you reverse it and then you just check to see if this is good, but there's still an inversion here, so I don't think we can do it in this case by just reversing one subsegment. But if it was just this, then you can, the first inversion and the last inversion match, so you can reverse that.
What about the 3, 4? Like, if you just reversed that out, wouldn't it be sorted?
Oh, you
Right.
would. That's right.
The last inversion would be the last 3 in the first 4.
Yeah, that is the last inversion. So you'd have to reverse this whole thing. And so yeah, so you figure out what range to reverse it, and check to see if it works.
Alternate solution is if you sort the list and find the first and last elements that differ. Works too.
Oh.
You copy it,
That
sort
does
it,
work.
find the first and last that differ. That's what you have to sort.
That's
Oh,
pretty
okay.
cool.
Yeah,
Yeah.
that makes sense.
Alright, cool.
Alright.
Thank you. Alright, who's doing F?
Sharon.
Welcome back.
A long time no see.
Hello, camera. So this is a problem I actually solved. So I know what I'm talking about. In this problem you're given, for each, there's n people. For each person, there's a number that relates to them spiritually. So for example, person 1 might relate to the number 1, and he might relate to the number 13. And person 2 might relate to the number 13, and person 3 might relate to the number 13. This is Atharva, and this is Jacob, and this is John, because they clearly have a common relation. But then you might have a person that likes 7 and 497. This is Andy. Actually, 71, I think, is his favorite number. Billy, what's your favorite number?
16.
And 71. Their names don't actually matter. But so you have these people and these numbers that relate them, and I think it's guaranteed that. I know. Actually, it's not guaranteed. You have to figure out if it's possible. If there exists some number relation so that they're all related. And some number relation, what that means is like person 1 and person 2 are related by the number 13. And you have to print n minus 1 of these relations so that everybody's connected, or say if it's impossible. So, because I use the terminology connected, this is a graph problem. And what we're gonna do is we're gonna make a node for each person and a node for each color. So for example, in this from this input, we would get a graph that looks like this. Node for each person, node for each color.
Oh, it's bipartite. It's also bipartite.
Hard to read. I'll use the orange. And what we're gonna do is connect the people to their colors. No. Well, actually, no, because the bounds are 10 to 5.
I know.
So like this. So what you can do is, if this graph is not connected, then obviously there's no way to connect some nodes. Maybe this is not obvious, but
Yeah, obvious.
actually it's pretty obvious. If you do some cases by hand, you might see that. And so let's say the graph is connected. The question is, how do we come up with these n minus 1 numbers? So one way to do it, and there might be a different way to do it. One way to do it is you start a DFS at node 1 and track for each node what its parent was. So 1 will go to this and to this, and then we'll just follow the DFS. Something like this. And what you end up having is you end up having a parent for each one, and it is easy to see. No, I'm just kidding. Then for every node, 1 does not have a parent, but every other one of these will have a parent, and its first parent will be a color, and the parent of that color will be a node that is already in the graph. So what we can do is print for all I, for all these I, we can print I, the parent of the parent of I, which will be a person, and we can print the parent of I, which will be the color that connects them. And that's the solution.
Alright, Jacob Magnuson, you want to do G?
Thank you. Time to learn how to solve this problem before I teach other people how to do it.
Can't even see that.
You have a strict 5-minute time.
Alright, yeah, 5 minutes.
Well.
That's
Dang,
5 seconds
that
wasted.
kinda
Yeah.
sucks.
Yeah, that's 1 minute.
No, I'll keep it short. So in this item, you've got these n elements that all add up to 1. So, all the way out here to n. We're going to select k of these elements. Say it's these 3. And we're going to replace each element with the sum of all of the unchosen elements before it. So this third element that we selected here, we'll get these and these at the end, because this is kind of like a circular problem. So these come around and all get added into here. This gets added to here. This gets added to here. So given the initial configuration of like the values in the boxes, and given the value of k that you're selecting, you want to know the actual effective expected value of each cell in this array. So the way to do this is we can just kind of compute the answer for each box separately. And the way that we'll do that is by considering the likelihood of runs to appear, where a run is a series of unselected boxes followed by a selected box. So like if we're looking at some box here, some like this box X, if we're going to certainly select this box and we want to know the probability that this cell contributes to X's box, that's the probability of this run appearing at this particular location to like contribute to that specific cell. So let's go over each of the cells and compute what that probability is. So we have this cell X, which is a particular cell that we need to be chosen out of all of the n cells that we select. So the probability of getting this particular X box, the probability of selecting this particular box at all in our configuration is k over n. Now that we know we definitely are going to have this box in our configuration, we want to know what the probability is that we don't select this box, and that we don't select this box, and so on. We need to not select some number of boxes before it. So if there are r boxes here in our run, we know that the run length has to be less than or equal to n minus k, because this is the number of boxes that we don't select in the array the entire time. But the probability of not selecting all of these every time is equal to the probability of selecting any box that's outside of this range. So we have n minus 1, because we've already selected 1, minus these range, these r boxes that we've selected. Yeah. Over n minus 1. And we take this out. So this is for selecting the first box in the run. And for the second, we again have to not select any of these r boxes. We want to keep clear out of the remaining n minus 2. And so on until you have n minus r. Yeah. And so this here is the probability of getting like a run of r. So what you can do is once you pre-compute that for every run length, you can go over n and n squared, go over each potential box x, and to compute its answer, you take the weight of like each of these times the probability of getting that run, and that total for x is the expected value of x. So like for all run lengths from 1 to n minus k, because that's the longest you can have, it's the value of x minus that run length times the probability of getting that run length. Yeah.
Really quick alternate solution.
Yeah.
If you have like some range, I mean it's just like easy to think about because we dark greened it. So
Please.
if you have some range, we want to know how many times, like we want to calculate the answer for this. So we're going to iterate through everything it could have come from. And then the number of ways that this square contributes to this square, like its total value is the value of this square times the number of ways you can pick some k that have this legal. which is just this size. So let's say this is like A, then it's A,
Choose k minus 1.
choose, yeah, k minus 1, because one of the ones is repeating this.
Gotcha. Does this get imprecise? Like when you're counting all those things, how are you like?
I mean, it's no bigger than this. That's like pretty much what this winds up being. But you
But that
can
can be.
yeah, you have to use doubles. Like, it doesn't overflow doubles. It goes up to like 500, choose 250. Which is why they made the bounds.
Would this
What they did?
stay accurate for like n squared for like 5,000?
No.
No.
It goes up to like 1,500 is the max you can do this with doubles for. And then after that, you either have to like be smart with how you do the n choose k or like doubles or something.
Okay.
The way we did it.
The way we did it, like if you pre-compute what the run probability is, you can keep it n squared,
Yeah.
and then actually go over the, like each cell, and then it's run, then it just ends up being n squared, because that you have you compute the probability per cell, like that, rather than counting all the ways that it can contribute to it.
I mean,
Like
we're
this-
still kind of doing it for cell.
Yeah, but
But that's still n squared, but it's like, if this avoid, you can do this in log to.
Mine's
keep it
just a
consistent.
factor of n choose k too big. Like, I just don't divide by n choose k till the end.
Well, you're doing your like arithmetic for like weighting proportions with doubles, counting n choose k for like.
Like, I calculate it for every square individually. I do like an n squared.
On each square.
For every pair of squares, yeah.
Yeah.
Like, for every square, I look at every other square.
squared.
I'm just saying like it would be inaccurate if you had like n and k up to 5,000. Probably, right?
I mean, probably, because, like, my things get order of magnitude of n choose k.
Without like big decimal.
Yeah, they just get really big.
Alright, so in H, you're this biker, and there's like, they map out this like terrain as these slopes, and you can be given, what are the bounds in this problem? I don't actually remember.
5 times 10 is 7.
I think it might be 10 to the 5th, or 2 times 10.
Good for n, 15 for k.
Yeah. What was it, 10 to the 5th?
Yeah.
Something. So you're given 10 to the 5th points that represent like the slopes of the land, and then you're going to be given k values, and they're going to give you this value in the form of a number with at most, or with exactly 1 decimal point after a number with 1 digit after the decimal point. I think exactly. And then they want you, for each of those values, to find like the longest horizontal distance that you travel like up a slope at this exact, at like this exact slope. So like, oh, stupid.
Well, at least that's what.
Yeah, stupid thing. They give you this in kilometers, and then they give you this in meters. But it's fine. And so like, you want to like, if you have some run from one point to another, then you just want to check if the endpoints are at least some slope, essentially. And you want to find the longest run of said slope, and they give you like 50 of them, which is like nothing. So if you want to check that 2 points are at least of the same slope, then what you can do is you can take the line that represents this slope that they give you, and then you can take these points and subtract out the corresponding value of this line that represents that slope, and then you'll end up with like all these adjusted values, essentially. And so maybe it might look something like that. And if you want to know that 2 points have like at least this slope, then you know for some point it has to have a y value, or greater. Because if it's greater, then it means it was like above the slope later on, so that's perfectly legal. If it's less than, then something like this this point would end up being smaller and lower in y value later on. So you can just adjust all the points based on that slope, and then you can sort all the points by y value. And then if you have all the points in, I guess I should go over an answer. The best possible answer will have an endpoint on one of the points they give you. That's important, because if you have an answer that's not like exactly on one of the endpoints they give you, there you can always slide it and either get a better answer or get an equal answer. So you basically want to try having each point as the endpoint for like your best run. And so if we're trying this point, say on this adjusted graph, then when we sort all the other points based on y value, then we look at all the points that are past us and find the maximum x value on this sorted list. Because if they have if they're above us in the list, then they have at least the same or equal y. And then if we want to find the furthest in one direction, we basically want to find the max x away from us in that region. And then if so I guess in this case it would be this guy. So this guy's x. You would get this point. The answer will be from, it'll like basically be this flat line from the point you're wondering that the endpoint is on for this answer, intersected with this point to the next point that it represents here. So you get this distance, and then you do the same thing backwards, where you look below you and then check for the min x away from you in the other direction. And then there's just two special cases where you end up finding the endpoint of the whole thing, and there is no next point to check the intersection with. So you just look at the index and notice that the index is either 0 or n-1, and then you just do like the integer distance. And you can do the max thing with a segment tree, but you probably need RMQ. Mine passed with segment tree after contest barely, but RMQ makes it way faster. And then you just do it for each k. So it's like nk log n.
Now that you mention it, you could also do a sweep down, right?
Could you do a sweep?
Like if you sort your points by y, you just want the rightmost one that's farther above you.
Mm-hmm.
So if everything you've processed is farther above you, you just want the rightmost one.
You totally could sweep. Yeah. So I guess you can get a really good nk solution to work.
Or I guess it'd be good long as you had a sort of, but it's a sort log.
Right.
It's a sort log.
It's a sort log. It's whatever. That's basically the solution.
You want to go next?
Give me another problem.
Alright.
That's a good one.
So the editorial says K is the next easiest, which I question the legitimacy of, but I'll do it anyway.
That's funny.
It's J, right?
It's as well.
So in problem K, you are kite surfing, and as any good kite surfer does, you have several islands that you want to jump over, and you're going to be in a race where you go from some start point to some finish point. You want to get there as short as possible. There are two things you can do. You can surf for 1 unit of time, which takes, I think, 1 second. Yeah, you can surf for 1 unit, which takes 1 second, or you can make a jump, which can be like any length you want, but it can be up to maybe t distance, or let's say up to j distance. And that always takes a specified amount of time, regardless of how far the jump is. So if you're in a jump, you might as well jump farther, is like the idea.
Yeah.
Which kind of makes sense if you've seen or like kite surfers actually jump. They're very floaty. So maybe this is like some optimal way of doing it. But then instead of this jump, we might want to just surf, right? So that's probably some optimal way of doing it. Obviously, if you land on an island, you can't surf, and you also can't land like in the middle of an island. They guarantee that it's possible, so you can always jump across somehow. So there are a couple observations. Oh, also very importantly, the number of islands is less than or equal to 500. And then like all of the numbers, like J, T, S, F, less than or equal to 10 to the 9. Alright, so a couple observations. The first is that if you have some island, you're going to need to jump over it. Let's say your jump is like this, for example. This is the island you want to jump over. It would make a lot of sense to jump earlier and earlier until one of two things happens. Either there's some island here, and if we jump any earlier, then we'd be jumping from the island, which we obviously can't do. Or there's, like, we land at the very end of an island. So if we do that, then we have this point we might want to jump from, which is right here. Now we have these 2 points, which are now relevant. We would never want to jump from the beginning of an island. Like, there's just no reason to do that. It's not helpful. The only reason we would want to do that is if that's like the perfect distance from the end of the island.
Or if there's another island up there.
Yeah, or if there's an island like right here.
Yep.
Yeah. I don't think that's allowed in, but
That's
like,
the thought.
there's no reason it shouldn't be allowed. Okay, so yeah, so that's the first observation. Second observation is, let's say we have some very long stretch of distance. And we're here, we want to get to here. If there's an island somewhere, then we have to jump somehow. So then we can like if we would jump and land on the island, we can split this up into 2 ranges. We can split it up into like to this point, or possibly to this other point, or just straight to here. So like, let's say we wanted to just jump straight, we would hit the island, so we can't do that. Then we can either like swim to here and then jump, or we can somehow travel to here, maybe just by jumping. But like, we can split this range up into like 2 sub-problems, basically, is the gist of it. But let's say there's not an island. Let's say we just have like some very large amount of water, or some amount of water with islands in the middle, but if we jump, we're not going to hit the islands. There are 3 ways we might want to do it. The first way is we might want to just jump there. And then this last jump is going to be a waste of time. The second way is we might want to swim the entire distance. And then the third and final way is you might want to jump a bunch of times
The rest
and then swim the very end. So these are the only ways you'd ever want to traverse some distance. So once we have those observations done, now the problem turns into a fairly common problem that we've seen before, which is named after 2 people, both fairly impressive computer scientists.
dynamic improvement.
No. One of which knew for loops. The other knew 2 more for loops.
Oh.
First one's name started with F.
Ford.
Dijkstra.
Ford Fulkerson.
Oh no.
Alright. I think those are 2 different people, right? Well, anyway.
Yeah.
We're going to do a dp of I
It's actually one person.
j equals the min distance.
Yeah, there's a dash there.
Yeah. So we're going to do a dp where we store where we're going from, where we're going to. Each of these are 2 of these 500, really they're 1,000 points. So it's n cubed on 1,000, but they're divided by 6s in there, so probably fine. So we know where we're going from, where we're going to. We need to check all of the islands in between to see, like, if we jumped, would we hit some island? And if you would hit some island, then you have to divide your range into subparts. So if you don't hit an island in between, there are just these 3 ways to travel. So you just take the minimum of all of them. You know, be figured out in ordered 1, obviously, with like division. That's it. Richard Peng says you can solve this with a segment tree, where the size of your segment tree is the jump length, and then you do like a sweep and math. So like each index here, each index here shows like the amount of time you would need to get to like this jump length part, and then when you have some island, you like zero out this range, and then like you do it at that base, so you like make a bunch of jumps. So like apparently you can solve this with 10 to the 6 pounds. I don't know. He didn't go into the details, but that's what?
Huh. He makes the claim.
Yes. Exercise left to the reader.
Hello, camera. I will now attempt to explain a problem. Having read the editorial in the last 15 minutes. Okay, so problem J, Jack Dawson proves. So in this problem, we have Code Forces blog, and there's comments, and we would like to make the comment chain aesthetically pleasing. What does this mean? Aesthetically pleasing means the first comment has a positive number of upvotes, and then the next comment has a negative number of upvotes, and then the next comment has a positive number of upvotes. and it has to alternate, so like one more comment.
Oh, the class. Wait a minute.
So so we're not given the comments. That would take too much work for the test data makers to make comments that are realistic. But we are given the upvotes. So what are we given? We're given n comments and the difference between their upvotes and downvotes for each comment. So for example, we're given 8, 8, 2, negative 2. So this by itself is not good. It doesn't alternate. This would have to be negative, or like maybe these two would have to be negative, and this has to be positive. The cost. Okay, so our solution to changing these is we make fake accounts, and for each fake account, it costs us some time. I think the time, like, let's call it C. And then we can also report a comment to Mike Mirzayanov and tell him this comment offends me, and this takes us our time, and we are very persuasive, so Mike will immediately remove the comment. We can always come up with some bullshit excuse to remove a comment. So we'd like to either make fake accounts where we can manipulate the votes by either upvoting or downvoting a comment, or we'd like to remove a comment by reporting it. The question is, what is the minimum amount of time that we need to spend in order to make this alternating? So we have some insights. If we have F fake accounts, then let's say F is 3, for example, here. Every comment with absolute value smaller than F can be changed to positive or to negative. So for example, this one, we can actually make it negative. This one we can make positive, so like these aren't guaranteed. This one has to be positive, If we had a 3, it would also have to be positive because we're not allowed to have any zeros in our common chain. So this would have to be positive, but these can change. So these would become wildcards. We don't know if they have a positive or negative delta. Following this, we basically have order and interesting numbers of fake accounts. What's an interesting value of f? For example, here I wouldn't want to have 5 fake accounts because it doesn't help me achieve anything that 4 fake accounts wouldn't help me achieve. With 5 fake accounts, these 3 things become wildcards, but I just made an extra account for no reason. I didn't gain a wildcard, so if I just had 4 here instead, then I can change these to be any delta I want and pay less, like spend less time making an account. So we have order and interesting values of f. In fact, like it's exactly n plus 1. Because we might want to make no accounts, or we might want to make, well, it's not exactly n plus 1, but it could be n plus 1. If every absolute value here was different, then we want to make value plus 1 fake accounts to make that a wildcard. So that's our first observation. What's our second observation? Okay. So suppose we had some, suppose this was set. Then in this example, let's say set to 4, and let's say there's like a negative 8 here, for example. So in this example, we have positive, positive, 3 wildcards, and a negative. We can see how many we need to remove between 2 things that are set. How many comments we need to remove. Between these 2, we know we're going to have to remove one of them. Because they're 2 positives and we can't change them. So let's remove them. Between these 2, we're going to have to remove one of the wildcards. Because this one we can make negative, and then this one we can make positive, but then this one we can't make positive or negative, so we can erase it. Actually, between any 2 non-wildcards, if there is an odd number of spots, we need to remove something. Yeah, if their distance is like 1. Yeah. So what can we do? We can pretend, like, so let's start with maybe f equals 0, and I think we can do some dynamic programming to tell us what the, for f equals 0, we have to remove all the zeros from the array, because we're not allowed to have any zeros, but we're not making any new accounts, so we're just going to find the longest alternating subsequence and remove everything else, and that will be our cost. Now, for all other interesting numbers, I think what we can do, and I'm not too sure because I didn't solve this problem yet, but I think a good idea would be to keep a tree set for non-wildcards, or let's call them knowns. And as we originally everything is not a wildcard, and as we iterate over values of fake accounts, things that become wildcards we can remove from the tree set. So and in this example, let's say we pick f equals 3, so then plus plus question mark plus minus. So we would remove these from the tree set, and then we would look at their so here we already know we are removing one of them, and we're looking at the adjacent ones, and we're going to see if we have to remove anyone here. And we kind of have to do these removal updates in order order 1 or log. It can be done. It is not explained how. So it's just implementation details.
So
But
if you have a range of question marks,
yeah.
you can like remove that range from your count, and then change the range and add one thing to it, and then add the range back in. So it's like a lot of maintenance.
Yeah, it's
Like you change parities of like what the offset of like changing one thing to a question mark is, right? How do you maintain that?
Like for a given range of question marks, you know what it contributes. It's either the number of question marks or the number of question marks minus 1. Like that's how many comments
Right.
you get out of it.
Yeah.
So you remove those, and now you have to add some range back in with that same that range of question marks possibly plus 1.
Okay.
Right.
Yeah.
So then, like if you have some range, maybe this contributes 7, and now we're adding this thing here, and like maybe we've got like some number here.
Okay.
So we remove this range conceptually from our counter. Now we have 7 less.
Yeah.
Now we add this back in, and now maybe this is a 2, so we count how many things this is. But these are both positive, so depending on the parity of this length, we either add like its length or length from this one.
Wait, so you're not affecting anything after that? You're just affecting
No.
like maybe a number before, a number after?
Yeah, you don't remove these numbers. You only remove question marks. There's
Yeah.
no reason to
Oh.
remove these numbers.
you remove question
I
marks.
see, I see. Oh, that's pretty neat. Okay.
So yeah, at this point, you go through the number of accounts you're creating and making the updates.
All right, speed round. 10 minutes to finish the problem review. Okay, so problem A, yeah. Let's do problem A real quick. So for problem A, you are competing in some tournament or something where people have points, and welcome. So you might have like 0 points, 1 point, 2 points, 3 points, and now you have a couple days. So like this is the start, and then this is going to be day 1, day 2, day 3. So initially, maybe you have someone who gets some point on day 1, they get a point on day 2, and they don't get anything to day 3. Somebody else maybe gets points like that, some third person. Some third person gets points like that. So you want to know, like, this person is in first place because they have the most points. They're in first place here too, they have the most points. This person's here, they're in second place, they're tied for second. Here they're also in second place, here they're in third place. So you want to know for all the people, or for each person, what is their average rank in the competition. You know that the total number of points everyone gets, because you have to read them all in, is like 10 to the 6th or something relatively small. And you want to figure out what is the average rank for each person across all days. So we're going to figure out the sum of their ranks across all days, divided by the number of days, so that gives us the average. So what we can notice is that each person might change like a bunch of times, or like a person might have the number of points they have change a bunch of times, but the total number of changes and the number of points any person has is going to be 10 to the 6th, because you only change your point value when someone gets a point. So for each person, we're going to iterate through all of their times they had a certain number of value of points. So this person, who's winning at the end, has 2 points for this whole time range. So what we want to know is for people who have 2 points, what is the sum of the number of people with more points in this time range? So that's a cumulative sum query. We want to know what's the cumulative sum of the number of people with more points in this range. Then we have this other range for this person, which is the 1. So in here, how many people, or like what's the sum of the people with more points on this day? And then the same thing for this. That's what we want for this person. Similarly, for this person, we want to query what's the sum of the number of people in this range above them. So it'd be 1 plus 1, so 2 total. And then we want to query this as well. And then for this person, they want to query this, and then this. So this, just to like kind of elaborate, I didn't draw it super well, but it would be 1, 2, 3, total. So we can build all these with cumulative sum arrays. So if you imagine we had a bunch of those, we're going to need one cumulative sum for each point value. There could be 10 to the 6 point values. Someone might get all the points. Actually, that's not true. There could be 3 times 10 to the 5th point values, which is an important distinction because it goes from MLE to AC if you do that differently. So you need like 3 times 10 to the 5th cumulative sum arrays. And then each array needs to be 3 times 10 to the 5th long, which is not going to work. But, as we mentioned, very few of these entries change, so we can store all the changes in tree sets, and then what the new values are. So if we only look at the interesting elements of this, there are only 10 to the 6th interesting elements. And then this MLE is in Java, so you can do some crazy speed ups by making it like array based and then binary searching instead of using a tree set, and then using int lists and long lists instead of array lists. So yeah, that's it. That's it. No, we've got several more.
We've got 2 more.
2 more. Okay. Go with whoever. Go.
When do you need to go?
I need to go in 5 minutes.
I thought Irv said he was
Okay.
going to be here.
He did say he was going to be here.
Okay.
I should have taken attendance. So that wrapped up.
Okay, so problem D is you're given a graph, and it's a weighted graph, so I have like some edges, blah blah blah. And you have node 1 and node n is up to like 2000, and number of edges is up to 10 to the 4th, I believe. And what you're gonna do is so like these edges have like some weight 1, weight 2, whatever. And what you're gonna do to this graph is you're gonna apply some transformation to all the edges, such that the weight of an edge. So if we call like L the length of an edge, you're gonna apply some transformation where you're going to take L, divide it by some value V, and add some value C. V and C have not been chosen yet, but that's the transformation you're about to perform, and you get to choose like what V and C values are. And so what you want to decide is, out of all possible like V and C values that you can choose, such that V and C are both like positive or non. Yeah, this can't be. So they're both positive. Which nodes will never show up on the optimal path from 1 to n? So first, I'll go through this pretty fast. So first observation is that if you have this transformation, this doesn't really matter. Like what you can do is you can just multiply this entire thing by v. What that implies is that if you have the graph, if you multiply each edge weight by some constant value, it's not going to change the optimal path. Because it's like you're like splitting each edge into like some constant number of like different edges, and the optimal path will like just be multiplied by the same constant. So you can multiply this entire equation. You can treat this as being like equivalent to just having like L plus C times V. So now what happens is like, now if you have like some path from 1 to n in this form, the L you can just like pre-compute right off the bat by doing a dp. Since you have like n and m are like pretty small, you can do a dp of what node you're on. And well, the second state I'll explain in a bit. Where's your car? And so this is like your path. What matters here is this value, c times v. You don't really care about what this value is, since this is going to be some real value. We can just call that like some like arbitrary big constant c. And if you have some number of edges, let's say we have m edges on our path. Let's see, let's call that x. If we have m edges on our path from 1 to n, then we're going to add this constant value that many times.
All of these variable name choices.
Thank you. And we can notice that this looks like a line. And in fact, each path for a different edge weight that's optimal can be represented as a line. So now what we want to know is, which nodes never, like the thing we're trying to answer is which nodes never show up on the optimal path. Well, if you take each path of like different number of edges as like a line, then what you're gonna have is, if you draw these out, you're gonna have like some upper envelope that's like, you're trying to minimize it. So you're gonna have like lines that look like this, blah, blah, blah. And you're gonna try to like walk this lower envelope and see which lines appear on that. If you know a line appears to be the best at some like interval, then you know that that number of edges is optimal. In which case you can just walk your DP and see which edges appear on the path. If an edge appears on the path, then both of the endpoints, like both of the nodes are valid. And they do show up on the path. So you can count the inverse of it. So this DP is pretty straightforward. You just go to the next node and try for like all edges. You compute like some value, like that's the minimum distance. And this is going to be your path length L. And the number of edges that you started off with is your value M. And X is like of the values that you're plugging in. So you get these lines. And for each line, you want to know if it ever is the minimum line. How do you know that? Well, if you look at like a line mx plus b, if we look at all lines with a slope that's, since we're trying to minimize like the lines, if you look at all lines with a slope that's smaller than it, and compute the first time you intersect with that line. So if the other line's like slope 2, if it's less than your slope, as soon as you intersect that line, this line is going to be better. So, and then if we look at all lines, M1, that have a slope greater than you, as soon as you intersect the last line, that means you're the best line. So let's call this range like L. Let's call this range R. Actually opposite. Let's call this R. Let's call this L. If L is less than or equal to R, that means your line is the best line for some like amount of time. It can be like exactly one point of intersection where it's like the best line, but it doesn't matter. As long as there's some point that is the best line, all those nodes and like that appear on that line can appear in your answer as like the optimal nodes. So for each line, you can find like these L and R values. If this is true, then this line is valid, and this number of edges works. So now we have a list of like edge lengths that work, starting from the like 1 to n. You know all the edge lengths that work. And to find out which edges actually lie on that path, you can do a DFS from the start. Like you can build back your DP by only following edges that appear on the shortest path. So if an edge appears on the shortest path for like that number of edges left, then you know this edge appears on the path, which means both of its endpoints appear on the path. And then you can just like have a visited array for which nodes appear on the path, and then count the ones that you've never visited. Those will never appear on the optimal path ever. And that's it.
All right, good job. So last problem, problem B. So problem B is your birthday, and you are given as a birthday present
An array.
An array.
Sure, an array, but you're taking the array and you're taking the liberty of turning this array into a balanced binary search tree. If you're solving this problem, you should know what a balanced binary search tree is, but we'll go over it just in case you don't.
Oh.
A binary search tree is some tree with the property that it's well, basically all the values are unique, and every value in your left subtree is bigger than, or is smaller than every value in your right subtree. So if there's a 1 in this tree, it's got to be here. This would be 2, 3, 4, 5. A tree is balanced if the depth of your left subtree and your right subtree differ by no more than 1. So this is balanced because for every subtree, so for every node, this has like a left depth of 1, right depth of 1, left depth of 2, right depth of 1. These are like 1 apart, so that's okay. But if we had something like this, then 0. Then this is alright because it's 1 and 0. This is alright because it's 2 and 1, so that's fine. this is 3 deep on one side, but only 1 deep on the other. So in order to fix that, we would have to add maybe some child here. And now that would be balanced. So the first thing we're going to do is we're going to pre-compute for every depth, what is the minimum number of nodes you need in order to have a tree that's that deep?
Wait, what's the problem?
Oh, yeah, probably. Okay. So you're given this tree, but it's a very generous birthday present, and you can't fit all of it in your house. So you can keep at most k nodes. No, keep exactly k nodes. You don't want to throw more away than you have to. Sorry, I spelled nodes.
Nodes.
You want to keep exactly k nodes, not k nodes. There you go. That's where the k was from. And you want, like, there are a lot of ways of doing that. You want the tree to be connected, obviously, otherwise it's not really a tree. And then you want the lexicographically. I think it's lexicographically.
It's lexicographically.
It's lexicographically for me.
All right.
Minimal set of nodes. So if you like sort the nodes that you keep, then like if you can keep 0, you want to keep 0. If you can't keep 0, well, fine. If you keep 1, you want to keep 1, etc. Right. So now to do this, what we're going to do is we're going to compute for every possible height. What is the fewest number of nodes that you need in order to make a balanced tree of that height? So for height of 0, it's just 1 node. For height of 1, you can do this. So it's that node. For height of 2, you would need to do this. For height of 3, well, your left child would be a height of 2. Your right child would be a height of 1. Okay? So we can take this node and put it here. We can take this and put it here. Now we have to add these 2 edges. So yeah, matrix expo, we only have to go to 10 to the 5th though, so it's pretty small. But we can just do it iteratively. You can do it matrix expo. So it's like the sum of, it's like Fibonacci basically, plus 1. Alright, cool. So we have that. We can pre-compute all these numbers. Now what we're going to do is we're going to, well, alright, here's the other thing. If we want the lexicographically minimal subtree, then we want to keep nodes that are as far left as possible. Because the things on the left are smaller.
Yeah.
Right? So we want to keep the leftmost thing we can. And then after that, we don't really care what we do, but we want the leftmost of the ones that are still available. So we're going to go through our tree in like left bias DFS order. And then every time we have some node, we're going to try and keep it. So let's say this is the first node we're going to try and keep. And then, yeah, we'll like worry about the other nodes. So if we need to keep this node, let's say we're going to add this node. So if we're going to add this node, let's say this is U. We're going to iterate through all possible parents, like all of our parents. We're just going to naively walk up the entire chain. And we're going to say for each parent, so let's say this is your parent V, if you include me, how much does the height change? So if you include me, the height would change by 1. So if the height changes by 1, that means we need to include, I guess, 1 more node. So that's kind of an understanding example. Let's say you look at this parent. If you include this node, to do that, you need like just the 1 node. To do this, you would need this 1 more node. The extra node you'd have to add. So you also would have to add me, so it would cost like 2 more, I guess. For this V, for 1 more example, well, the height used to be 3, so if the height was 3, then you would have needed this node here. So now if you include me, you're going to need this node here. You're also going to need this node here. And you're also going to need me. So this would increase the height by 3.
Okay.
So basically, if we can afford that, we have like a certain number of k nodes left, right? If the number of nodes this would cost to add me is small enough, then we would add me.
Yeah.
If it's not small enough, you don't have a choice.
Okay.
So that works really well for this first path. So now we have like all of these nodes on the leftmost that we're going to add. And we have these other nodes that we've promised we're going to add, but we haven't actually added them.
They also might not exist, right?
They also might not exist yet. We might not have added them.
Okay.
But like we've paid for them.
Okay.
So now we're over here. When we're here and we go to our left child, or like our parent who's less than us, whenever we do that, we know that this parent has already paid for us.
Okay. I guess they always exist. This case it's guaranteed by balance, right? To start with.
Yeah, it's guaranteed to be balanced.
So they exist. Yeah.
So, like this parent, if we add ourselves, it wouldn't change our height.
Right.
Well, no, they might not exist. Like, they might not exist because we might not have added them. The only things that exist are ones we've added.
But
We
like
start
they-
with an empty tree.
But they exist in like the given tree.
Yeah, they
For
exist in the
sure.
given tree.
Okay,
Yeah,
yeah.
because
Okay.
it's balanced.
Right.
So here we have this parent, so we can add ourselves because like it's free.
Mm-hmm.
And then the same thing for this node is also going to be free. But like maybe this guy over here, well this guy should also be free, or it will cost 1 or whatever. But yeah, you kind of get the point.
Mm-hmm.
So that's kind of the idea. What's the runtime? Well, we have n nodes. For each node, we have to iterate through all n or all of our parents, and then we have to do a bunch of math. All the math is order 1.
Do you
So-
actually need to iterate through all parents? Isn't that just
You
what
can
we-
actually not do that.
Can't you just like use the numbers we pre-calculated? Because like if we know we're at certain depth.
Well, like some of your parents, there's a way to get around it. I don't understand what that way is. You can do it. You can do this in linear time, but the way to get around it involves like the order that you process the nodes. But like you can't just do this because for this node, it matters that these nodes exist.
Okay.
Like if you were given a tree where these didn't exist and you didn't already buy them,
Mm-hmm.
then like you might have to pay a different amount for this node.
Okay.
So that's why you have to iterate through your parents.
Sure.
So it seems like it'd be n squared. For every node, you iterate through itself and all its parents.
Yeah.
Conveniently, it's a balanced binary search tree, so it's log
Oh,
tall,
log D.
so you only have log parents.
Classic.
Alright. Yeah, so though that's that problem. I don't totally understand the math. I haven't implemented it. Like I get kind of the idea.
Yeah. It makes sense.
There's some implementation details to work out there.
Yeah.
So that's it. Thank you for coming to the problem review. Alright, I thought everybody wanted to tell everybody to subscribe.
Like, comment, and subscribe.